Hello, this is Charlene. In this video, we're going to be talking about conditional probability and the multiplication rule. The first things we need to talk about are the independent and dependent events. Our information here tells us that independent events are independent if the occurrence of one does not affect the probability of the occurrence of the other. And it also tells us that dependent events are dependent if the occurrence of one of them affects the probability of the occurrence of the other. The bottom line is that if we have two events, probability of two events, the probability of the second event will not be affected if they are independent events. And conversely, if they are dependent events, the second probability of the second event is affected by the probability of the first event. So we need to just keep those together, that independent means that it is not affected by the first event. And dependent is affected by the probability of the first event. So it's going to make more sense as we move through the video, and we're going to come up with some examples that will hopefully help you understand this better. Example 1 is going to help us understand and to determine whether the events are independent or dependent. It says that we're going to select a king. Selecting a king is going to be event A. So let's go select a king. So right there is a king, and I'm going to pull it out of the deck of cards. Well, the deck of cards has 52 cards in it, an entire deck, but we pulled one out. So when we pull one out, guess what changes? The total number of playing cards goes down to 51, not 52, because we are not going to put that king back in the deck. Okay, so that means that we're now going to go look for a queen, and the queen, pulling a queen out of the deck is considered event B, the second event. So let's go find a queen. So there's a queen, and I am going to pull that queen out of the deck. And so now I started with 52, and after I pulled the king out of the deck, I only had 51. So it changed. So the thing is, though, is that pulling the king out, which was event A, changed the total number of cards to 51. So that affects the total of number of cards that I'm choosing from when I take my queen out of the deck. So that means that my event is going to be dependent. It is going to be dependent because when I pulled this first card out, it changed the total number of cards that was left because I did not put that king back into the deck. So when it's a dependent event, the total number changes. So our event is going to be a dependent event. Event B is going to be dependent upon the first event A because the total number of cards changed. The total number does change when it is a dependent situation. Our next example says that we are going to toss a coin and we're going to get a head. And then it also says that we are going to roll a six-sided die and obtain a 6. So tossing the coin and getting a head is considered event A, and rolling a six-sided die and getting a 6 is going to be event B. Okay, so I roll this dice, or I'm sorry, toss the coin and I get a head. Okay, so I get a head. That's it. Does it have anything to do with that six-sided die? No, there is literally nothing that flipping this coin has to do with rolling this die. So over here, I'm going to roll the die and I'm going to get a 6. So I had how many choices for tossing the coin? I had 2 choices, right? So I got a head. I had one head, and I had options of 2 choices. I either could get a head or a tail. So that total number is 2. Over here, when I roll the die, I get a 6. Well, 6 is 1. There's 1 6 in on the six-sided die, and I had a total of choices to get a number of 6, total of 6. So the thing is, though, this number of 6 has nothing to do with that right there. So they are completely separate from each other. They are completely independent. So these are independent of each other, have nothing to do with each other, no effect whatsoever. So independent, but we need to remember that when they are independent, the total number does not change. This total was 2. This one is 6, and they do not have any effect on each other. Now let's talk specifically about conditional probability. A conditional probability is the probability of an event occurring given that another event has already occurred. We write it like this: the probability of B given that A has already occurred represents the probability of event B occurring given that event A has already occurred, and is read probability of B given A. So we write the probability of B given A like this. And then this is a specific formula. We've got a formula that we can work with when we're talking about conditional probabilities where one probability depends upon another probability already having occurred. And it is the probability of B and A divided by the probability of A. But a practical way to think about that is like this: the probability of B given A is equal to the probability of the intersection of those two events. You might also think about it as being the overlap of those two events, where both they are both the same, both occurring at the same time. And then that is divided by all of the given. So this is going to become helpful in helping you to remember how to deal with given probabilities, conditional probabilities where something is given. The probability of B given A is equal to the probability of both of them happening at the same time divided by all of the given event. Now let's introduce the multiplication rule. The basic multiplication rule is used for finding the probability of A and B. The probability that event A occurs in a first trial and event B occurs in a second trial. So the general rule that I like to think about is that when we have the word and, it means that I am going to multiply their probabilities times each other. So it is the basic multiplication rule says that if I have the probability, I want to find the probability that A occurs and B occurs, I'm just going to multiply the probability of A times the probability of B. Now, there's a different scenario. If the outcome of the first event A somehow affects the probability of the second event B, such as in a given situation, it is important to adjust the probability of B to reflect the occurrence of event A. So the first event is affecting the second event, so it's going to change the second probability. And this is how we would show that equation. The probability of A and B is equal to, again, the probability of A, except now it's being multiplied by the probability of B given A. So this piece of our equation reflects the fact that something is going to change. The sum total number is going to change in the second probability. Probability. So this is known also as a dependent situation. So we've already talked about independent and dependent probabilities, and this is what this is talking about. It's like we're going to use the probability or the multiplication rule when we got the probability of A and B. However, if it is a dependent relationship between the first event and the second event, then it is going to change my second probability. So here is the original. If they are independent of each other, it is just the probability of A times the probability of B. But when it is dependent, the second probability, that second total number, is going to change. Another way to think about dependent is without replacement. And we had the example where we took a king out of a deck of cards. We did not put it back in, and it made the queen dependent upon the king because we had changed the total. So we write that if A and B are dependent, the probability that the two events A and B will occur in sequence is this equation. Of course, we've already looked at that in the screen before. This probability is calculated by considering that event A has not replaced and there is one less possibility. Okay, so independent events are with replacement. Another way to think about it is with replacement, which means that the total number does not change. It stays the same. If A and B are independent, then the rule can be simplified to the probability of the first event times the probability of the second event. Okay, so now we're going to be looking at a bag of marbles because marbles is something that you can take marbles out of the bag and you can leave them out and then choose more marbles, or you can put marbles back in the bag. So that's why we're going to use a bag of marbles. It's a good way to look at this idea of independent or with replacement probability. So our example says that we are to find the probability of a blue marble and we are to find the probability of not a blue marble. That's what this notation right here means. The line over the blue means the probability of not a blue marble. And you may remember that from other videos. Okay, so now I need to point out something though. We're talking about replacement and whether a second event is dependent upon a first event. But the way that they've asked this question, it is not this question. This right here is where they're blue and not blue are occurring and affecting each other. This right here, where it says the probability of blue, they're just asking us what is the probability of blue. And then separately, they're asking us what is the probability of not blue. So these two things are not equivalent. So do not confuse those. Like I said, we're talking about this, and we are going to deal with some questions here in a minute that have to do with this independence with replacement situation. But they're referring back to just a simple probability here. So a simple probability is just going to be a part out of a whole. So the part out of the whole. So how many blue marbles do we have? Well, I have, let's see, let me pull my list, my bag of marbles. All my marbles are all notated here in this box. I've got four blue marbles. So that means I have 4 blue marbles. And then how many total marbles do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've got 4 out of 9, and that is a simplified fraction. So that is the probability of getting a blue is 4 out of 9. And separately, they are asking us what is the probability of not a blue. So all of the ones that are not blue are all the red and all the green. So I have 1, 2, 3, 4, 5. So the probability of not a blue is going to be 5 out of 9. So those are the two probabilities that they're asking us for. Now, I want to point out also that this not blue is considered the complement of the first one, blue. So if you add those two together, 4 9s plus 5 9s, you will end up with the entire bag of marbles. And when you've got a probability and the complement of the probability, they will always add up to 1 whole bag of marbles. Okay, what is the next one they're asking us about? Okay, they're asking us about the probability of getting a 3 and the probability of getting not a 3 when we pull marbles out of the bag. So again, this is not the and situation. This is not multiplying probabilities. Up here, we had the probability of blue and not blue. If they are inside the parentheses together like that, that's where we use the multiplication rule. This is not the multiplication rule because the and is not inside the parentheses with the probability. So we're just getting two simple probabilities. We're doing a part and a whole, and a part and a whole. So the probability of getting a 3, well, how many 3s do I have? I have 1, 2 3s. So the probability of getting a 3 on my marble is 2 out of a total of 9 marbles. And the probability of getting a not 3 is all the rest of the marbles. So that would be all of these plus this one right here. So 1, 2, 3, 4, 5, 6, 7. So that's going to be the probability of not a 3. The complement is going to be 7 out of 9. And again, complements add up. So 2 plus 7 would give you 9 out of 9. And that would be one whole bag of marbles. So I've got probability of a 3 is 2 out of 9. And the probability of not a 3 is 7 out of 9. Okay. And again, this one also is just a simple probability. It's a part out of a total. So how many 5s do I have? I have no 5s. So that means that I have 0 5s or out of 9 choices, but 0 out of 9 is just 0. So I have 0 probability of getting a 5 because none of the marbles have a number 5 on there. So the probability of getting a 5 is 0. Okay, and this one says they want us to find the probability of getting a number less than 5. Okay, so numbers less than 5. Let's see. All of these are less than 5. All of these are less than 5. And all of these are less than 5. So that means that my part of the whole is 9 parts out of 9 total marbles, which means that my probability is 1. And of course, that in practical thinking is 100%. There's a 100% chance that I'm going to get a number less than 5 out of my bag of marbles. Well, now it's going to get interesting. They want us to find the probability that you're going to draw a blue marble given that it has a 2 on it. The formal equation is the probability of B and A divided by the probability of A. Another way to think about that is the probability of the intersection of B and A, the first event and the second event, all divided by all of the given. So we are going to calculate the probability of both because that's another way of thinking about the word intersection. The probability that they're both a blue and a number 2 on it. So we're going to do the probability of both. So what is the probability that they are both blue and a 2? Well, there is one blue marble that has a 2 on it. So there's my blue marble with a 2 on it. So I have a 1 out of 9 probability that they will be both blue and 2. So then the probability of a 2. Well, how many 2s do I have? I have 1, 2, 3, 3. I have 3 2s. So that is a 3 out of a total of 9 marble chance. Well, how do I divide a fraction by a fraction? Well, I take the numerator fraction and I multiply it by the reciprocal of the denominator fraction. So instead of 3/9, it's going to be 9 over 3. Then I can cancel my 9s, and that gives me a probability that we're going to draw a blue marble, given that it has a 2 on it, of 1/3. So that is the probability that we're looking for. However, I'm going to show you a shortcut. So we've got this fraction divided by a fraction, and we do this work, but we can shortcut. we can still think of it as the probability of the intersection divided by all the given, which is the probability that they're both blue and 2 divided by all of the 2. Well, how many marbles do I have that is both blue and 2? Well, I just had that one blue 2. So one of those and all of the 2s. And of course, all of the 2s was 3. So there you go, 1/3. So we can shortcut straight to the 1/3 and just save some time here. So we can go straight here by just considering both blue and 2 divided by all of the 2, and you get 1/3. Okay, let's go to the next one. Our next one says that they want us to find the probability that we have a marble with a 2 on it, that is given that it is already blue. Again, formal equation is the probability of B and A divided by the probability of A, but we can think of that as being the intersection over all of the given, or we can shortcut it even more and say both a 2 and a blue marble. So what is both blue and 2? Well, again, that was just one marble. So that can be 1 and then all of the given. So all of the given is all of the blue. So how many blues do I have? Well, let's see. I have 1, 2, 3, 4 blues. So that means that my denominator is going to be 4, and that is the probability. The probability that I am going to draw a marble with a 2 on it that also happens to already be blue is going to be 1 out of 4. Okay. Our next one says they want us to find the probability of a red marble given that it has a 3 on it. What is our shortcut? Our shortcut says we're going to find the probability of the intersection where they are both red and 3. Okay, let's look for both red and 3. There's both red and 3, so I only have one of those. One red that's also 3, and then we want to do all of the given. Well, it means all of the 3s. So how many 3s do I have? Let's see, I have 1, 2, 3s. So that means that my probability that we're going to draw a red marble, given that it already has a 3 in it, is a 1 out of 2 probability. Okay, one more in this section. We're going to find the probability that we are going to draw a marble with a 3 on it, given that it is already red. Again, what is my shortcut? I'm going to find both 3 and red. So both 3 and red is going to be, there's a red 3 right there, so there's only one. And then I want to do all of the given, which is all of the red. Well, all of the red, I've got 1, 2, 3 reds. So that is going to be 1 out of 3 probability that we're going to draw a 3 marble that also happens to be red. 1 out of 3. This video has been brought to you by Connect the Dots Online Math Tutoring. Before you leave, click on the like button and the subscribe button, and have a wonderful day.